We spent some time over the last couple of days talking about what we now call the law of conservation of mechanical energy. We learned about kinetic energy and potential energy. Mechanical energy is the sum of kinetic and potential energy. So it's the kinetic energy plus the potential energy. The law of mechanical energy tells us that mechanical energy can't be created and it can't be destroyed. It can be transformed from one type to the other. It can be transferred from one object to another. But the total amount of energy, if we examine everything, if we take into account everything, the total amount of energy will always remain the same. Now, there's a whole lot of places in physics where we apply the law of conservation of energy. In physics 20, at least starting off in this unit in physics 20, we apply the law of conservation of energy typically when an object is experiencing a change in height. So for instance, maybe we're dropping an object straight down and we want to find its speed as it hits the ground. Maybe we've got a roller coaster problem where the roller coaster car is going from the top of a hill to the bottom of a hill. Or maybe we've got a roller coaster problem where it's going from the bottom to the top. Or maybe we've got that swinging boat ride problem where it's swinging back and forth like this. Okay? When there's a change in height, we can use this law of conservation of mechanical energy that says the total energy remains the same. Well, how are we going to use it? Well, mathematically, a statement that says energy has to stay the same is going to be phrased like this. EI equals EF. The energy that we start with at the beginning is going to be equal to the energy that we end with at the end. The total initial energy equals the total final energy. All you got to do at this point, once you've written down that mathematical statement of the law of conservation of energy, is ask yourself, what kind of energy do I have at the beginning and the end? So ask yourself really two questions, both here and here. Do I have a height? Okay, if the answer to that is yes, then I have potential energy. MGH. If the answer is no, then I don't have potential energy. Ask yourself the second question, is the object moving? If the object is moving, then we put in kinetic energy, 1/2 mv squared. If the object isn't moving, then we wouldn't put in mv squared, 1/2 mv squared. Now you do the same thing afterwards, at the end of the problem. Do I have a height? Yes, kinetic potential energy. No potential energy. Is it moving? Yes. All right, then there's kinetic energy. If it's not moving, then no, there's not kinetic energy. So potentially, you could see it written as long as this. But a lot of times, most times in fact, we're missing one or two of those terms in there because we don't have a height or because we don't have an object that's moving. We had two questions for homework last night, and that was on worksheet number 5, your conservation of energy worksheet. I'd like to take a look at both of those questions, and then we'll set you free to work on a couple of more questions, and then we'll see where we're at after that. Question number 1 on that worksheet says a student on the roof of the school throws a 500-gram ball off the edge of the school at a speed of 15 meters per second. If the ball is moving at a speed of 24 meters per second when it hits the ground, how high is the school? And we're asked to describe the energy transformations that are taking place here. That description is not a mathematical thing. It's just qualitatively, all right, what kind of energy do we have? What's increasing? What's decreasing? What's it being converted from? What's it being converted to? Let's deal with the math first. There's a change in height of this ball, right? It falls down toward the ground. And if there's a change in height, we are allowed to use the law of conservation of mechanical energy. Doesn't mean we have to. There's other options, right? We learned those yesterday. But we're allowed to use EI equals EF. Now, let's ask ourselves those two questions at the beginning of this problem. In the beginning of this problem, we're going to make at the top of the school, on the roof of the school. What kind of energy do we have at the top on the roof of the school? Is the object moving when it's on top of the school? What's the answer to that question? Is it moving? It looks like it is actually. Throws a ball at a speed of 15 meters per second. As it leaves the roof of the school, it's moving, right? So since it's moving, what kind of energy do we have there? Yep, kinetic. So let's put in a term 1/2 mv squared. Initial, V initial squared. Now, Ollie, I'll ask you this question again. Is there a height when you're on top of the school?
Yes. No,
When you're on the roof of the school, are you at a height?
Yes.
Yes, yes, you are. So what kind of energy do we have as a result of that height? Yeah, good. So we're going to say 1/2 mv squared plus mgh. We've got an object that's moving. We've got an object that's at a height. So we've got both kinds of energy there. When the ball hits the ground, is it moving? Jamie, is it moving when it hits the ground? Not after it hits, but as it hits the ground, is it moving? Yeah, so it's got kinetic energy, right? Because it's moving. We'll make that 1/2 mvf squared. So Rose, when it hits the ground, is that at a height when it hits the ground? No. So there isn't any potential energy as it hits the ground. There's our term, right? Remember we said the last slide there, we said we could have up to 4 terms in there, kinetic potential energy on both sides. We got 3. Okay, sometimes we have 2, sometimes we have 3, sometimes we have 4. Mass cancels because it appears in every term. Let's sub in some numbers and see what we get. 1/2 of the initial speed, that's 15 squared. We don't know what the initial height is, but that's what we're trying to find, right? How high the building is. VF is 24.5. Notice we're plugging numbers in before we rearrange this time. This is about the only time that I suggest you do that, but I think it is useful to do that this time. All right, 1/2 of 15 squared is 112.5 squared. Sorry, it's 112.5. And 1/2 of 24 squared, I'm not sure what that is. 288. How are you going to solve for HI there? Ethan, what are we going to do? Yeah, get rid of what's not attached, right? So let's take that over by subtracting. 9.81 times HI equals 288 minus 112.5. Gives me 175.5. And we're going to divide that by 9.81 now. What do you end up getting there? Matt, do you have that? 175.5 divided by 9.81. 17 point. Okay, thank you. 17.8 meters. The height of the school is 17.8 meters. Not the only way to solve that problem, right? We could have used VF squared as equal to VI squared plus 2AD and solve for D. This is one more tool in the toolbox. Let's talk about the conversions. Oh, is that right? It's not 288. What is it? All right, sorry, that works out to be 300.125. Thank you. Take the, wait a sec, what's going on there? Should be up here. 300.125. Take the 12.5 over by subtracting, and then divide by 9.81. And what do we end up getting now, Silveros? 19.9? 19.1? How many people got that one? Good. Is that all right? Does that make sense? Now, they do ask us to describe the energy transformations that are taking place as well. Well, when we start off at the top of the building, we start off with kinetic and potential. As it falls towards the ground, we're not destroying any energy or not creating any energy, but we're converting from one type to the other. What's the conversion that's taking place? As it falls, potential energy turns to kinetic energy. Potential energy decreases, kinetic increases, so it's a conversion of potential to kinetic in that case. 2 says a ball was dropped from a height of 60 meters, 60-meter high building. How fast is it moving when it's fallen halfway down to the ground. It's a conservation of energy problem because we do have a change in height here. What kind of energy do we have in this one to start off? Is there a height? Yes. Aiden, so that means we got what kind of energy? Good. Is it moving when it starts? No, it's not. So there's no kinetic, right? My initial energy is just mgh initial. What about at the end of it, when I've gone halfway down, 30 meters down? Is it moving now? Yeah, it is. So I've got what kind of energy, right? Is there still a height? Shivetta, is there a height now? There is. So there's also potential energy as well, right? Once again, the mass cancels. There's a couple people in the hallway last period during spare asking me about the mass. Hey, is that a typo? We don't have a mass for this? No, it's not a typo. Okay, I mean, typos happen, right? But not in this case. We don't need a mass because it ends up canceling out. If you've got a mass and you plug it in, that's fine, but you don't need to. All right, what do we got here? 9.81 times the initial height of 60 equals 1/2 of VF squared plus 9.81 times 30 meters. 9.81 times 60, we're going to take this term over to the other side by subtracting. When we subtract those, I think we get 294.3, and then we divide it by 1/2, and we're going to get 588.6. And we're going to square root that, and we're going to get, I want to say like 26, 27, somewhere in that range. 24. 24.3 meters per second. What's the energy conversion that's taking place here? The exact same as in question number 1. It's kinetic, sorry, it's potential to kinetic. It's just that it doesn't finish in this one. Okay, in the first question, it's all kinetic energy at the end. In this one, it's only half kinetic energy, half potential. Okay, Hannah, question? We're okay with rearranging that? Okay. Okay, here's what I'd like you to do right now. Take a look at question number 3. There is a little typo in this one, question number 3. It should say the 2.5 kilogram rock is dropped straight down from the top of the building. How fast is it moving when it's fallen 10 meters? See what you can do with that question at your desks here right now, okay? Everybody look up here. We'll take a look at question number 3 now. It says a 2.5 kilogram rock is dropped straight down from the top of a building. How fast is it moving when it's fallen 10 meters? How much time is elapsed? We won't worry about the time so much right now. We'll worry about the fall of it and the final speed of it. The final speed of it right now. The conservation of energy part of it. Okay, in the end, what do we know about this question? Does it change in height? We're allowed to use one of those group B equations that we learned back in Unit 1, but we're also allowed to use this new tool that we learned, conservation of energy. So let's set it up that way. Let's say EI equals EF. Now, here's the tricky thing about this one. Here's the tough thing. We know that it falls 10 meters, but we don't know where it fell from. What was its initial height, and what's its final height? I want you to think back to what we said the very first day we introduced energy. We talked about kinetic energy and various types of potential energy. And when we got specific and talked about gravitational potential energy, we said that there always must be a blank for potential energy. You guys remember what that is? Two words. Yeah, there has to be a reference point. And you remember what we said? We can make the reference point whatever we want as long as we're consistent and as long as we specify what it is. Here's what I want to do for this question. I want to make my reference point the bottom of the fall. We drop it. It falls 10 meters. Now, maybe it falls another 30 meters past that. Maybe it falls another 50 meters past that. Maybe it falls another 2 meters past that. Maybe it doesn't fall past that at all. Maybe that's the bottom. It doesn't matter. What we want to do is make this our reference point. If we make that our reference point, what lies below that is irrelevant. Basically, our reference point is the ground, or at least we're making it the ground. So if that's our reference point, then we have clearly potential energy when we start, because there's a height, and we said it was dropped, so there is no potential energy, sorry, no kinetic energy at the beginning. At the end, it's moving, so there's kinetic energy. But if we define that as a reference point, there is no potential. Does that make sense? We could have defined our reference point down here, and there would be potential at the end. We'd still get the same answer, but I think it makes sense to just define the zero potential energy as the bottom here. So this is what we got. Masses cancel. We're left with 9.81 times the initial height, which we're saying is 10, equals 1/2 of v squared. 98.1 divided by 1/2 is 196.2. Square root that is, what is it? 14, exactly. Okay. .0 meters per second. Let's give you one more question. Try question number 5, please, on that sheet. All right, this one says a 0.75 kilogram ball was thrown straight up into the air. The ball reaches a max height of 17 meters before it comes back down. What's the initial speed of the ball? We're not analyzing the trip up and down here. We're going to analyze just the trip up, like we did in a couple of problems back in Unit 1 in our Group B problems. So we're going to analyze the trip up. If we do that, we're going to say, because there's a change in height, we're allowed to use EI equals EF. And we're going to say at the beginning of the problem, it's moving. Right? Clearly, it's got to be moving, otherwise it doesn't go up into the air. It's moving, therefore it has kinetic energy, 1/2 mvi squared. Does it have a height at the beginning? When I throw it from ground level, does it have a height? No, so we're not going to say, we're going to say there's no potential energy there. But at the end of it, as it goes up into the air and slows down, and stops momentarily, as kinetic energy is transformed into potential, is there potential energy at the end? Sure there is, yeah. So we're going to say mgh final. But it's stopped, so there is no kinetic energy at the end. Now we have the mass, so we can plug it in there, or we can just cancel out the m's. Makes life a little bit easier. We're looking for VI. And H is 17 meters. 9.81 times 17 divided by 1/2, and then we got to square root that. What does that end up being? V squared is equal to 9.81 times 17 divided by 1/2, or you could have multiplied by 2. I was walking around, at least one person forgot to square root there. You don't forget to square root that. What do we end up getting? 18.3. Okay, I'm going to give you one more that's not on this sheet, all right? One more that's going to be just a drawing of a situation. It's going to look a little bit different, but we're going to treat it exactly the same way. So here's the problem. Here's your little roller coaster. It's at a height of 50 meters above the ground. It's got a speed of 5.0 meters per second. I want to know how fast that roller coaster is moving when its height is now 12 meters above the ground. So it's most of the way down the hill. How fast is it moving when it's most of the way down the hill? What's VF? See what you can do with that, and then we'll check that over before the end of class, and that'll be it. This problem looks a little bit different than the problems that we've been working on, because this one doesn't involve the object going straight down or straight up. But because kinetic and potential energy are both scalars, it doesn't matter what path they take. The direction is irrelevant. Okay, this object, hey, moving at 5 meters per second, we want to find out how fast it's moving when it's 12 meters above the ground. If it went straight down, it would be moving at exactly the same speed, 12 meters above the ground. It's irrelevant whether it's straight down or at some funny path like this, or at some funny path like this, 12 meters above the ground. How it gets to that point doesn't matter, as long as there's no friction, that is. So how are we going to do this? Same way as we solved our other problems. We're going to say EI equals EF, conservation of energy, change in height, right? We have an initial potential energy because there's a height. You ask yourself, is there a height? Yes. Potential energy. Is there speed? Yes. There's kinetic energy. At the end of the problem, which is not the ground this time, but rather most of the way down, is there a height? Yes. There's still a 12-meter height. And is it still moving? Yes. So there's still kinetic energy. Masses, once again, cancel. They seem to always cancel with these ones. If mass appears in every term, then it cancels. Sub in some numbers here. 9.81 times the initial height of 50. The final height is 12. What do we got here? 9.81 times 50 is 490.5. 5 squared is 25 times a half is 12.5. What's 9.81 times 12? 117.72. All right, so now what we want to do is add 490.5 plus 12.5. It's 503. Take the 117 over by subtracting. 503 minus 117.72. That gives us 385.28. Thank you. On the left-hand side equals 1/2 VF squared. We can divide by a half or multiply by 2. Gives me 770.56. 770.56. And then we're going to square root 770.56, which is going to give me somewhere in the range of 27 meters per second. 20, what is it? 27.7, 28 meters per second. Sorry, 27.8. Still rounds to 28 meters per second, right? There we go. How many people got that? Good, good. Listen, guys, we got a unit test on this on Wednesday, right? If you're struggling with this at all or with anything else, see me, please. We got a couple of days of school left before we have that test, right? See me about that. You also know that you have your unit assignment due on Monday. There's one of these on your unit assignment. Good practice. Come and see me Monday, scheduled help if you're struggling with that. Okay? Get it handed in Monday. Get it. Do it as best as you can. Okay? Don't just hand it in and say, it doesn't really count for much. Hand it in, use it as good practice. Okay? See me if you have trouble with it.